Let's go ahead and get started. We have a unique conjunction, to borrow the astronomical term, this morning, with our speakers here before the break. Our tutorial lecture today will be given by Sigrid Klose, who happens to be a former PhD advisee of this year's CEDAR Prize Lecture awardee, Mears Oppenheim. Sigrid Klose is an assistant professor in the Department of Aeronautics and Astronautics at Stanford University, where she heads up the Space Environment and Satellite Systems Laboratory. Prior to joining Stanford, she was a project leader at Los Alamos National Laboratory and a technical staff member at MIT Lincoln Lab, where she led a program to characterize meteoroids and meteoroid plasma using high-power radars. She's received, among others, the Presidential Early Career Award for Scientists and Engineers, PCASE, and the Award of Excellence from the United States of America for exceptional efforts in meteoroid plasma analysis and modeling. She has also been co-host of the TV program Known Universe in 2011, which aired on the National Geographic Channel, and has been featured as a guest expert on PBS in 2013 and 2014, and the Weather Channel in 2015. So, as you can see from her bio just now, her PhD advisor, as her PhD advisor Mears points out, she's always juggling a dozen projects. Trying to focus Sigrid on a single project is like trying to move a tornado with a fan. So in other words, she's the force of nature. Please join me in welcoming Sigrid this morning.
Good morning, everyone. Thank you, Sabani. Thank you, Mears, for that nice introduction, and thank you for the opportunity to speak to you here today. So the topic of this tutorial is actually still a bit of a mystery. It's both not well understood and yet still actually quite controversial. And this mystery is basically, how can a particle no larger than the size of a grain of sand, so something you could barely see, cause an anomaly or even a catastrophic failure of a spacecraft? Okay, so CEDAR community, we all know that spacecraft live in a very complicated plasma environment, and it varies both spatially and temporally. And we often think of it as beginning at the lower boundary of the ionosphere and extending outward. And we know it contains energetic charged particles and electromagnetic and ionizing radiation, but it also contains solid particles. And this includes things like asteroids, really big particles, meteoroids, as well as space debris. And we know that this spacecraft can get affected by these particles, primarily through charge-particle interaction. But the question is, can the solid particles, again, things that are about the size of a grain of sand, also cause electrical issues through impact ionization? Okay, so what are these particles? So let's begin by just defining what do I mean by a solid particle, or what we term a hypervelocity particle. There's really two main categories, and again, we're talking about particles that are quite small. And the first are the naturally occurring meteoroids. So meteoroids tend to go very fast. They travel between about 11 and 72.8 kilometers per second. That lower limit is just the Earth's escape velocity. That upper limit is a sum of the Earth's orbital velocity and the solar escape velocity. But thanks in large part to a lot of researchers here in the CEDAR community, we now found that the speeds are actually quite high. On average, they go between about 30 to 60 kilometers per second. Before the advent of these high-power large aperture radars, we thought the speeds were actually quite a bit less. The densities tend to be either icy if they're associated with a comet, or a little bit higher if they're associated with an asteroid. And the size, again, really, it's a distribution. So you can get things that are less than 62 microns, which is what we technically term dust, up to about 0.3 meters, 1 meters, which is called asteroids. Anything larger than that's called an asteroid. And then the other spectrum of the hypervelocity particles is all the junk that we've actually put up there. And I'm sure many of you have seen the movie Gravity. And so this is, again, things that get put into orbit unintentionally, and we call it either orbital debris or space debris. And the speeds, as you can see, tend to be a lot less. It's about 12 kilometers per second in low Earth orbit. And on average, it goes about 7 to 10 kilometers per second. So you can see immediately that space debris tends to be about almost an order of magnitude slower than the naturally occurring meteoroids. Because this is human-made material, the densities tend to be higher. But just like meteoroids, you get this distribution in sizes where you can get something as large as a rocket body to, again, something smaller than a grain of sand. And we really have to worry about all of it because, again, the particles are traveling so fast that when they impact, they can cause damage. And the questions we're trying to really answer are, what's the probability of impact? Where are these particles? Are they in orbit? How fast are they going? And then again, importantly for our research is what happens when these particles actually impact a spacecraft. So we can talk about the sources of these particles, and again, getting back to the meteoroids, these are naturally occurring, and these tend to be associated with a parent body, either an asteroid or a comet. So some of you may have heard about the Chelyabinsk event, which happened back in February of 2013. This was an asteroid that was about 20 meters in diameter, going about 20 kilometers per second, that initially weighed over 10 to the 10th grams, or about 12,000 metric tons, that, unbeknownst to us, was entering in over Russia, over Chelyabinsk. And so what you're seeing are some videos from the dash cams on the cars in Russia, which many of the cars over there have these dash cams due to security reasons. And because of this, we got some really great visual images on this particle coming in, this asteroid. And we're able to not only get a velocity, because we again had many cams that were able to actually detect it, but we were also able to get a general idea of what was the parent body. What was scary about this event, though, is that we had absolutely no idea that it was coming in, and no prior knowledge, because it was just too small for us to detect using our telescopes and other typical observations for detecting these asteroids. So in addition to asteroids, as I mentioned, meteoroids also can be associated with parent comets. And actually, most of the showers that you hear about, the Perseids, the Leonids, are actually associated with the parent comet. And so there's two main areas. There's the Kuiper belt between about 30 and 100 AU, as well as the Oort cloud out to 50,000 AU. In terms of space debris, again, it's all the human-made stuff that we've put up there, but there have been two main events in recent years that have really contributed to the overall population. And the first was the, going back actually most recently, is the Iridium satellite, Iridium Cosmos collision, which happened in February of 2009. So the satellite Iridium-33 and Cosmos 2251 actually collided. And again, we didn't have the ability to accurately predict that these two objects were going to collide. There was some foreknowledge that there was a low probability that these two objects might collide, but it was low enough that the satellite owners and operators decided to actually not do any type of maneuvers. And so what happened is that it created, obviously, a bunch of debris. And that, in addition to the Chinese ASAT test, which occurred in 2007, means that between about 600 and 800 kilometers, we have quite a bit more debris than we did before these two events took place. And so the way we categorize these, or kind of group these in order to get a better understanding of these parent objects, is really quite different between the meteoroids and the space debris. For meteoroids, we tend to group them into either what we call the showers or the sporadics. So the showers are specific for a parent body. Again, they're associated either with a particular comet or a particular asteroid. And they're named for the radiant, which is the point from which these particles appear to emanate. So the Leonids, which occur every November, look like they're coming from the constellation Leo. Contrast that to what we call the sporadics, which is kind of the quasi-continuous background. And these tend to be grouped by location, where they've been kind of gravitationally focused within our solar system. So you'll see some like north toroidal, south toroidal, north and south apex. So the big difference is that the showers, again, people have heard about the Perseids, Leonids, tend to get all the media coverage, but it's really the sporadics which occur every night, and we see a peak in the flux at about 6 a.m. as the Earth's kind of plowing through this debris stream, which are the real threat to satellites. And I just want to highlight that because that's really, again, something that was discovered by the CEDAR community and something that the satellite owners and operators really weren't aware of. They thought they only had to worry about the meteoroids during these particular times during the year. And again, for space debris, we don't really group them according to the same categorization as meteoroids, obviously. But what you do see is if you plot the number of objects as a function of year, and sorry, the font's a little fuzzy here, you'll see that they do break them up into things what we call fragmentation debris, really small objects, rocket bodies, and then again, talking about those two events, the Chinese ASAT test and the Iridium Cosmos collision, means that our total flux has increased quite a bit just over the last few years. And this is really known as what's called the Kessler Effect, which just means the more objects we put in space, the more debris we're creating, the more likelihood that we're going to create more debris, either through just the shedding off of particles from these objects, or again, through these types of collisions. So if we want to look at the overall flux of these particles, this is now both the meteoroids and the debris, we can plot the flux in per square meter per day as a function of the mass of the objects and kind of give you an estimate about what size particles should we worry about, how many particles are there, and how big are they. And so what you see in here, the blue curve is the Gruen curve. This is a meteoroid partly modeled, partly data. And then the other colors here, masters, are the orbital debris, again, model plus data, at different altitudes, spanning 325 up to 625 kilometers. And what you'll notice is as you get to bigger particles, the space debris tends to dominate. And again, it gets a lot of the media attention, so people tend to think that meteoroids aren't as much of a threat as space debris. But as you get to smaller and smaller objects, you'll notice that they come comparable, and actually the meteoroids actually even dominate. And so in the past, NASA, and actually many people in the space community, have set this threshold of what size particle do we actually have to worry about that's going to hit a satellite and potentially cause some type of damage. And it's about here at 10 to the minus 3 grams. So we've really only worried about this size in the past when we were looking at satellite threat models. And if you notice here, I said here about a nanogram-sized particle will impact a square meter spacecraft about once per day. But the question is, do we have to worry about these small particles? What about the size range in here, down to about 10 to the minus 9 grams? Are these still things that could potentially cause damage? And so there is some historical evidence that small particles can cause damage, both mechanically and electrically. And we can start all the way back with a very famous story about Mariner 4 in 1967. And it was, I believe, in mid-September 1967, Mariner 4 was actually on its way back from Mars. It had already completed its mission, which was to photograph the surface of Mars. And it sent back the first images of Mars showing craters, not life, as many scientists had hoped. And Carl Sagan was quoted as saying that this was the most disappointing moment of his life, since he had hoped that he would actually see Martians. So in September 1967, when Mars was about midway between Earth and Mars in its heliocentric orbit, its impact detector, which is meant to characterize how often the spacecraft was hit by meteoroids, suddenly detected about 17 hits over the course of a 15-minute period. And during this period, it also experienced about a 1-degree drop in temperature, and it actually changed its attitude slightly. And so people were very puzzled because they had no idea what was happening. It recovered from that event, but unfortunately, just a couple months later, the same thing happened where it detected over 83 impacts over the course of about almost a day, a little bit less than a day. The same thing happened in terms of attitude. It changed attitude. It had some attitude perturbations, but it also experienced a severe degradation of signal strength such that the spacecraft was actually considered lost. And it's now in a defunct heliocentric orbit and communication was terminated. The interesting thing about this event is that we still today do not know exactly what happened. The best theory that's been put forth is that it actually encountered kind of a dead comet, what we call a dark comet, and a debris stream, but it hasn't been detected since then. However, if you look to more recently, there's definitely been a number of, I would say, unexplained anomalies and kind of circumstantial evidence to suggest that these really tiny particles actually can cause loss of either a failure on board or a loss of the entire spacecraft. And so I've listed just a few of them here. Probably the most famous is the Olympus communications satellite, which during the peak of the Perseid shower, which occurs every August, experienced a loss of gyrostability. So it started spinning, and then unfortunately, they expended all their fuel trying to recover it. And so it was considered a total loss. So this, even though it never detected any kind of momentum transfer, so they weren't sure that they were hit, it occurred during the peak of a major meteor shower. So again, the best hypothesis or theory out there is that it actually was hit by a Perseid meteoroid that then caused some type of electrical disturbance to cause the gyro to be lost. More recently, in 2009, Landsat 5, also during the peak of the Perseid shower, also experienced a loss of gyrostability. They were able to recover, so the satellite is still operational, but again, no momentum transfer, so no direct evidence that it was ever impacted by anything. So if it was impacted, it was by something extremely small, and again, it didn't cause mechanical damage, it caused some type of electrical event. ADOS 2, let me skip Jason for a second. ADOS 2 and ALOS both experienced complete power failures. ADOS 2, it was during the Orionids in October in 2003. And then ALOS was in 2011, also experienced a complete power failure during the Lyrids meteor shower, which occurs every April. And again, no momentum transfer, and these were both, again, considered complete failures. So the last one I want to mention is the Jason-1 satellite, and this actually did detect an impact. Its semi-major axis changed by about 30 centimeters, and then immediately following this, it experienced power anomalies for about 5 hours. Jason-1 is in a 1,300-kilometer orbit, which is an orbit, again, known for a lot of space debris. So I mentioned before that it's the sporadic meteors that we have to worry about. I'm mentioning specific showers this time, again, just because we know definitively that there was heightened activity during that time. Whereas if you just take any particular day, we could say that, oh, it could be something associated maybe with magnetosphere, something with even perhaps the ionosphere, but not necessarily the meteoroids. And so, again, these are just 5 examples, but what we've done is we've been able to get access to the NGDC database, which is basically just the no anomaly database for US satellites in MEO and GEO orbits. And we looked at about 5,000 satellite anomalies over a 20-year period or so from 1972 and 1992. And one of my students was able to basically categorize what types of anomalies are happening on orbit. And what was surprising was, first, that there were these many anomalies happening on orbit, and secondly, how many of them were categorized as unknown. So some of the things that they will report is something like deep dielectric charging, a very high-energy particle can make its way deep into the spacecraft. Surface charging, where you're just basically building up some surface charge and then discharging it. Single event upsets, but again, most of the majority of the particles, or I'm sorry, of the satellites, actually were tagged as having unknown anomalies. So a few years ago, when I first arrived at Stanford, we started to investigate this process and said, okay, well, we know when these macroscopic particles, either space debris or meteoroids, impact a satellite, it can cause mechanical damage. But I'll tag that as well known, even though there's still active area of research. Think of a bullet puncturing some type of material. These are associated with the larger particles, and therefore, remember that flux plot, these tend to be very rare, so obviously unlikely to occur. But the smaller particles, the ones smaller than 10 to the minus 3 grams, even maybe potentially smaller than 10 to the minus 9 grams, could potentially cause some type of electrical anomaly, either a discharge or even perhaps creating a plasma that can radiate. And because these are smaller particles and very fast particles, they're much more numerous and therefore much more likely to impact a spacecraft. So again, rule of thumb is a nanogram-sized particle will impact square meter about once per day. And the question became, can we diagnose this phenomenon? Do we have to worry about this potential mechanism? And so the 2 areas that we investigated, one was the electrostatic discharge, which again built up of charge on the satellite. This particle comes in and discharges it. But the other more nefarious area that we investigated was actually creating an electromagnetic pulse, very similar to what's actually created during a nuclear detonation, which is one of the things that I investigated when I was at Los Alamos. And so this is actually a movie put together by one of my students, Andrew Nuttall, showing how when a particle comes in, it creates this very bright ejecta, this plasma. And again, we're kind of focusing on, can this plasma, as it's expanding out into the vacuum, actually radiate? And could that wave potentially get into the spacecraft? So a few years ago, I was a member of the National Academy's panel looking at this potential risk. And I won't read all the words here, but just kind of want to draw your attention to what I highlighted in blue. So when we're looking at meteoroids and debris, we not only have to now worry about the larger particles, but we also have to worry about the small ones, and in particular looking at the effects from that plasma being created from the very small but very high velocity particles. And so in order to characterize the satellites, this is a very big project. We need to do this from using both remote sensing in order to really get an estimate of what types of particles are out there, what are their sizes, how fast are they going, where are they coming from. So flux, mass, and velocity, using high power large aperture radar to detect the particles coming in and creating the meteor or the plasma. But then we also have to do some ground-based testing and actually try to replicate or duplicate what's actually happening on orbit. So what you see here is just one of those ground-based facilities, which allows us to actually detect the RF emission, and looking at, can we characterize the impactor? And then once the impactor actually hits the spacecraft, can we characterize the effects? And the 2 of those together, in addition to whatever spacecraft specifications, such as the charging environment, how large the spacecraft is, what type of orbit it's in, will finally allow us to fully understand the electrical damage potential. Okay, so the rest of my talk, that was a very long introduction, but what I will go is briefly go into some of the data and how we actually characterize the population, looking at what we call impacts in the atmosphere of the plasma. And then I'll talk about some of our theory and results from impacts on spacecraft. Okay, so again, mentioning the CEDAR community, there's been a lot of active research in this field here in the past 15 years. But the general idea is, as you saw with the Chelyabinsk event, these particles are constantly coming in. There's about 100 billion particles greater than a microgram that enter Earth's atmosphere daily. And these particles are tiny, they heat up, and then they ablate off atoms. And then the parent particle, as well as those ablated particles, collide with the background neutrals and create plasma. And this occurs nominally between about 70 and 140 kilometers. It depends heavily on the speed of the particle as well as the mass. But we group these plasmas into two distinct categories. The tail, which is that shooting star that all of us have seen, it goes on for kilometers, as well as the high-density plasma that occurs right around the meteoroid, which we typically call the head. And there's been many efforts to try to simulate what these particles actually look like. Professor Oppenheim, my advisor, who will be speaking next, is actually, I will say, the world expert in doing this, so I won't speak too much about it. This is a particle and cell simulation that we put together at Los Alamos a few years ago, just showing this tiny little microgram-sized particle at the center here, and then we have the electrons and ions and neutrals kind of extending beyond it. So in combination with collecting these data, as well as doing simulations, we've made a lot of headway into really understanding how do these tiny particles actually create this plasma in order to help us actually diagnose what we're detecting. And so, as I mentioned, high-power large aperture radars have, I would say, been the premier instrument, type of experiment that we've been using in the past decade to try to understand these plasmas. Prior to about 1990, we would use low-power radar, which gave you a broader field of view, but not as much resolution, and also different population. It was a larger size. So this is the Altair radar, which is stationed out on the Kwajalein Atoll. And what we found is that anytime we were actually pointing up, and this radar is primarily used actually for space surveillance, we would detect these plasmas. And so this is a movie of what you would see. This is actually the plasma. This is signal strength basically as a function of time at two different frequencies. And again, if you're opening up your range gates in that sweet spot between about 70 and 140 kilometers, you can see these plasmas pretty much all the time, especially at 6 a.m., again, when the Earth is kind of sweeping up these debris streams. And so one of the reasons why we use the Altair radar is because it is dual frequency and also has really high range resolution and is able to give you a really great data set in terms of, again, understanding the parent properties. But of course, there's many other fascinating, wonderful radars that we can use to do these meteor studies. Arecibo Observatory has been one of the premier, again, facilities, and it obviously is the biggest single dish, and it has a ton of resolution, high range resolution, as well as sensitivity. And it's also at a slightly different frequency, and we use that to try to, again, understand the scattering properties. The MIT Haystack radar has also been used. Phil Erickson and others have been able to do some studies on, again, understanding the velocities and the altitude distributions. And then also, Asta Pelnin-Wanberg and her team have used the iSCAT radar as well. And so again, I just want to kind of give you a sampling. This is obviously not all-inclusive. But just to speak a little bit more about Altair, again, one of the reasons why we've used this radar in the past is because it is dual frequency, as I mentioned. It's also extremely well calibrated, and it has interferometric capabilities, which means that we can not only tell you the range rate, but we can actually tell you the 3D velocity of the particles. And so just to give you a couple specs here, the range resolution is about 30 meters at VHF or 7 meters at UHF, and the sensitivity is about 64 dB at VHF or 81 at UHF. And the type of data, again, you saw the movie a few slides ago, but if you take a snapshot of that, we can create these things called range time intensity profiles. So altitude or range on the y-axis, time on the x-axis. And this, again, gives you kind of an indication of what type of meteor data is actually being created. So it's a little bit hard to see, but this is the head echo. Again, that's the plasma immediately around the meteoroid that moves at the speed of the meteoroid. And then the trail, this is called a non-specular trail, which extends out behind. And the trail, again, some interesting plasma physics, primarily moves due to the velocity of the wind. The head echo we've used quite extensively, again, because we're focusing on understanding that parent meteoroid in order to do spacecraft threat characterization. So getting the exact position of that meteoroid as well as the speed and deceleration is important. And so one of the kind of challenges in understanding these data is how do you take a signal strength from a plasma and then again correlate it to properties of the meteoroid such as mass. So one of the things I did many years ago with Professor Oppenheim was to develop this scattering model to try to correlate the signal strength of the plasma, again, with the meteoroid properties. And so what we did is we basically came up with a model to talk about how the plasma is distributed as a function of distance from the meteoroid. So you see here plasma density decreasing as you get further and further out from the meteoroid. And then correlate that with some reflection coefficient associated with whatever radar you're using. And so we were able to come up with a model that tells you what the peak plasma frequency or density is as a function of radius, color-coded for either this reflection coefficient or the radar cross-section. And what you see again is that as these plasmas become bigger than the wavelength, which is, again, we're using VHF, it's about 160 megahertz, the signal strength should go down, as well as basically this altitude dependence where you're seeing higher altitudes or higher velocity particles ablating higher up, which is where you're going to create this really high or big, large plasma. And so after we are able to actually correlate a radar cross-section to some peak plasma frequency, we can then use what the community's basically done is basically use some ballistic parameters where you're conserving momentum between the meteoroid and the air molecule to then be able to definitively tell you what the mass, radius, and density is. And so if we have a way to correlate the radar signal strength or ionization, electron ionization to the mass, we can then also use the conservation momentum to use the mass and get you a radius. And then from there, we can use both of those and assume it's spherically distributed to get you a density. So again, for the first time, we were able to definitively tell you not just what this parameter, the mass over the cross-section is, but what the mass, the radius, and the density are. And so the methodology, again, using that data, is pretty simple. You can take the angle or the interferometric data as a function of altitude for both your azimuth and elevation, and then take the range rate data, which is the component of the velocity along the radar line of sight, and use the angle data to actually get you a 3D or an actual velocity. And then again, using these basic models, take these data and actually plot what the meteoroid mass is as a function of altitude, as well as the meteoroid radius. So again, remember, we're detecting the plasma, and then we use the models to correlate the signal strength of the plasma to some plasma density, which then allows us to use those equations to back out the parent particle. So again, John Matthews, Diego Hanches, as well as others in the community have been using this technique and this technology to basically, for the first time again, actually tell you what the parent particle properties are. Okay, so again, that was kind of just a very brief introduction to impacts in the atmosphere, and we're using those to get things like the flux, again, the masses and the densities of the particles. But the tutorial, or really focus of the research since I've been at Stanford, has been on really understanding what type of plasma is being created by these particles, and how do the spacecraft specifications, the charging of the spacecraft, potentially cause any damage. So for the last part of the talk, we'll focus on impacts on spacecraft. I'll briefly go over the theory, talk about some space experiments, and then end with some ground experiments. Okay, so this very simple movie kind of gives you an indication of what we think is happening when these particles actually impact a spacecraft. So you have a meteoroid debris impact your spacecraft material. That bright flash is meant to simulate or demonstrate the plasma that's created. And then you have your electrons and ions and a very small component of neutrals expanding out into the background vacuum. And what we believe is happening is that after impact, after your electrons and ions are formed, the electrons having a lower mass have a higher thermal velocity and will escape first. Then the ambipolar electric field will pull those electrons back and actually inhibit their motion and enhance the ion motion. And this whole particle, this whole plasma is actually expanding out at the isothermal sound speed while these electrons are oscillating around that ion front. And so this is the basic idea behind what we think is happening when these, again, tiny particles, 10 to the minus 9 grams, 60 kilometer per second velocities are impacting a spacecraft. Okay, so no mechanical damage, we have just a little divot here, but creating plasma that could then potentially radiate. And so there have been others in the field that have actually looked at a similar mechanism. This is an equation by McBride and McDonald back in 1999, looking at just how much charge is being generated when these particles impact spacecraft. So this is the charge generated in Q, and it scales basically as mass, first power to velocity to 3.4. Although this exponent varies depending on which facility you're actually using and which paper you're actually quoting. But you can see it has a very strong velocity dependence. So if you plot the log of the mass as a function of velocity color-coded for charge, obviously the higher velocity particles, higher mass particles are going to produce the most charge. But then the question becomes, how do you actually take that charge and turn it into a plasma density and then also potentially a radiative mechanism? So this is a plot of plasma scale length as a plot of velocity. And we've looked at three different basic, or I should say the community's looked at three basic parameters to try to determine what that plasma density is. And the first is just the crater depth. How much of that spacecraft is the particle actually taking out? How much is it ionizing? The second is the radius where local thermodynamic equilibrium breaks down. And then the third one is the Debye length, which is a measure of the shielding within the plasma. And unfortunately, we really don't know what the scale length is, I should say, but you can see that it spans about 6 orders of magnitude. So what we can do, though, is use these parameters as possible estimates and try to get an estimate of what the plasma density is as a function of that plasma scale length. And so what I have here is basically your plasma density has some peak plasma density, and it'll get expanded at that isothermal sound speed, and it'll, again, scale with that particular plasma scale length. From this basic equation, we could then look at what is the potential frequency as a function of velocity. And again, we could use a couple of different parameters. We can look at what the plasma frequency is at the radius, again, where that local thermodynamic equilibrium breaks down. Or we could also look at the radius of the impact crater, and we can model this again and then compare it to some of our data. The dynamics is very basic. What we've basically done is just used an F equals ma equals QE equation. So this C is just the acceleration term, which is scaling with the distance between the electrons and ions. Remember, the electrons extend out first. And so what you see here again is your peak plasma frequency modified by this distance between your particles, again expanding at that isothermal sound speed. And so we can get an estimate then of what that distance actually is, and then put it into the Larmor formula in order to get an estimate of what the power radiated is. And so this equation becomes an exact solution, but since we believe that the expansion rate is much slower than the thermal speed, we can just use the WKB solution. And then again, get an estimate using the Larmor formula. So again, I know it's very equation heavy, but all I want to point out is basically this is scaling with your thermal speed, with your plasma frequency or your plasma density, and also is heavily dependent on whatever that initial plasma scale length is. And so you take this equation, you plot up the radiated power as a function of a normalized frequency, and what you immediately find is that the power emitted by, again, these very tiny particles creating very small local plasmas is actually quite high. So these are three different scaling lengths. This is a normalized factor. This is the plasma frequency times that scale length over the expansion speed. And you can plot this either for a slowly oscillating plasma, again, the oscillation associated with the electrons, or for a quickly oscillating plasma. Or you can also plot in terms of a spectrogram where you have the frequency versus time. And again, what you're seeing here is a chirp-like pulse where basically as you're going out further and further in time, the lower frequencies are being emitted. So it's very much, again, like a nuclear detonation where you have this impulse and all the frequencies are being emitted at a single point in time, but are getting to that sensor or are expanding out according to whatever the frequency component is. Okay, so this was some of the theory actually put out by our group, as well as there's a couple groups in China, as well as actually a group at JPL. But again, there was very little data to kind of support this radiative mechanism for these very tiny particles. So again, quoting Carl Sagan, nice hypothesis you have there, be ashamed if someone were to test it. I published this paper in 2010. There was a lot of pushback, I'll say. And so what we did is we started looking to try to get some data to actually corroborate some of the theories that were put forth by the community. And there have been certainly a few that have been put out in orbit. The first is the LDEF, in low Earth orbit, I should say, the Long Duration Exposure Facility. And so this was a mission that was basically meant to just characterize what happens when particles impact spacecraft. And so it was sent into LEO by Challenger in 1984, and it was picked up by Columbia in 1990. And what they were basically able to do is correlate, this is a pretty simple equation, of the diameter of your crater to the diameter of your particle, looking at the density ratio of the particle to your target, and then modified by a velocity. So again, another empirical equation. And what they're able to do is basically look at how LDEF was positioned to get an orbit, as well as the size of those craters, and then relate it back to actually what the particle was. And what they found is that it matched pretty well. This is the number as a function, or number flux as a function of crater diameter in centimeters, to what I would say some of the more well-vetted models were at the time. So you have blue and meteoroids, meteoroids in blue, red is debris, and then the LDEF, which again is showing that as you get to smaller and smaller particles, it's not really actually matching what people had predicted. LDEF is certainly not the only one. As I mentioned, Mariner was one of the first to actually detect these streams. But there's been a number of different types of spacecraft that have been up detecting particles, all the way getting back to Pioneer 8 and 9. Most recently, Cassini. This is a table that was published by Srama et al. Just a few years ago. But what Srama quoted, which I found interesting, is that way back in 1983, people knew that these types of particles were actually creating plasma. And the quote is, surprisingly, the plasma wave experiment on board Voyager actually picked up charge signals from expanding plasma. And it was generated by these dust impacts. So there was some suggestion in the community that this was an actual real phenomenon, and it kind of faded away over the last 20-some years before actually a few of us started looking at it again. Okay, so we have some space-based data. It's very sparse. It's not, I would say, well vetted in the sense that we're not sure how to actually interpret some of the data. And so what we've done is we've turned to some ground-based facilities. And the advantage is that these are controlled experiments where we have knowledge of the impactor, but the disadvantage is that it can't fully reproduce the particle parameters in space. And so this is a plot from Lee et al., which is basically showing projectile mass as a function of impact speed, or projectile diameter. And we have up here orbital debris, which tends to be a little bit bigger, and again, remember 7 to 10 kilometers per second. And then the meteoroids, which really travel between 11 and about 72 kilometers per second. But these ground-based facilities are really unable to fully reproduce these particles. So you can see electrostatic accelerators can kind of get at the very smallest meteoroids, but can get the right velocity regime. Light gas guns can kind of overlap a little bit with orbital debris. And so what I'll be doing for the last part of this talk is showing you some results from accelerators and light gas guns, but just kind of, again, keep in mind that we're not fully reproducing the population that we actually detect when we're in orbit. Okay, so there are limited facilities around the world to, again, try to duplicate or replicate what actually happens when these particles impact spacecraft. But the first, again, are these accelerator facilities where you basically have a bin of dust, you charge it up, and then you apply some potential to accelerate these particles to very high speeds. And so, again, the downside is that we can replicate meteoroid speeds, but the particle sizes are orders of magnitude smaller than what we detect in orbit. So this is a plot of particle mass as a function of speed. And again, because we're applying a constant potential, you can see this trend where the highest velocity particles are correlated or associated with the very smallest mass particles. And so in the community, I would say the two that have been used most frequently are the Max Planck Institute, and then just recently the Colorado Center for Lunar Dust Acceleration Studies opened. It's a fantastic facility. And we've been able to use both these facilities to, again, try to reproduce these results. Additionally, there are a few light gas gun facilities around the world. NASA Ames Vertical Gun Range, AVGR, is one of them. The White Sands Missile Range is another. And this is more used to reproduce orbital debris speeds. So here's some of the data from AVGR. This is particle mass as a function of speed. And again, you can see we're about an order of magnitude lower in speed and quite orders of magnitude higher in mass. So again, this is about 5 to 6 milligrams compared to about 10 to the minus 15 grams for the accelerators. Okay, so the basic idea when you use these facilities is that you have some type of vacuum chamber, usually about 1 meter to 2 meters in diameter. You have some type of spacecraft material that you can mount, and then you have your sensors that you can put in the chamber to actually detect this radiating plasma. So the idea is that a particle comes in, hits your target, again, think 10 to the minus 15 gram particle, creates this plasma, it expands out into the vacuum, and is detected by a number of sensors. So we have things like radio frequency sensors or patch antennas. We have some type of plasma sensor, things like a transient plasma analyzer, retarding potential analyzer, and some type of optical sensor. And we keep that chamber at vacuum, again, to try to simulate or reproduce what's happening on orbit. So the types of sensors that we can use, one of them is shown here on the left. This is what's called a transient plasma analyzer. And it's basically just meant to detect the charge that's being emanated as this plasma is actually expanding out into the vacuum. You'll notice that it has a bunch of different grids and wells. And again, what we can do is basically pre-select what type of particle we want to see. So we can pre-select the energy range and also pre-select whether we want to detect electrons versus ions. On the right here, again, is just a setup where you're showing this photomultiplier tubes or spectral PMTs, some of the plasma sensors, as well as these patch antennas. And so it's a very complicated, kind of all-inclusive experiment. We're not the only ones to do this. Again, the people of Swarmer et al. In Germany have done a lot of these experiments as well. But as I mentioned, it's very complicated. We're trying to detect not only the optical signal, but the plasma signal and the radiated emission as well. So we have patch antennas spanning 165 up to 916 megahertz, so about 9 antennas, multiple plasma sensors, and then 3 or more photomultiplier tubes. The targets were donated by Lockheed Martin. Lockheed expressed interest in this project many years ago. And so the idea is that what we would do is we would be able to take some of the targets given to us by Lockheed and actually be able to, again, fully reproduce what's going on in space. So we had some tungsten, which is a high-density material kind of used as our control. We had aluminum. We had solar panels, solar cells, optical solar reflectors, and then we also had active Efield sensors, which we use to bias the targets to, again, kind of reproduce what's happening in space to, again, capture that idea that these spacecraft are actually charged in a charged environment, and we can bias either positive or negative. Okay, so once these plasmas are actually formed, there's a number of different scenarios that can actually occur in terms of how the plasma is expanding. So if we bias our spacecraft positively, the blue is going to be the electrons, the red is ions. We have a particle come in, and again, because we have a positive bias on our target, we're going to be basically shooting those ions out from our target and into our sensors. If we have a negative bias on our target, again, meteoroid or space debris comes in, you're going to have a much faster electron population that's actually expanding out. If we have a neutral bias or a grounded target, again, meteoroid or debris comes in, you have both the electrons and ions expanding out and, again, oscillating about that ion boundary. So again, it's a very simplistic picture, but it kind of gives you an idea of how does the spacecraft specifications or the charging actually affect the expansion of this plasma. Are we primarily going to detect ions, electrons, or will it be a combination of the two? And so some of the data that we've published out in the community, again, lots of data to show, many sensors, has shown this effect of detecting either the electron population or the ion population. So this is data from a 40 kilometer per second particle going about 10 to the minus 15 grams. The grid was biased positively, so we had a target and then a grid, so we're basically ejecting electrons out. And what you found here is that this is basically telling you, yes, you were impacted by a particle. This is the optical signal showing, again, that when this particle is impacting the spacecraft, you're creating this plasma and this flash. The plasma sensor also detected net charge when the plasma is expanding. And then all of these data, which I want to draw your attention to, is basically the radio frequency emission from the plasma. And I want to highlight this again because this is, I believe, the first time this was ever detected. And it was actually seen by one of my students, Teresa Johnson, who was part of the CEDAR community a few years ago. And we were sitting at the oscilloscopes, and I had my sponsor there, actually, and we were not sure that we'd actually be able to detect any RF emission. And there was a lot of discussion about the type of signal processing we'd use to pick it out. And she saw this and said, oh, that's funny. And we didn't believe it at first, that this emission would just be so obvious. So again, you might know about Asimov's famous quote, "The most exciting phrase to hear in science, the one that heralds new discoveries, is not eureka, but that's funny." And that's exactly what happened here. So first time we saw radio frequency emission from these plasmas. Okay, so then just to kind of finish up the talk, I just wanted to show you some of the sample plasma data again from out in the literature. So this is retarding potential analyzer data showing that dependence on bias, showing again how we bias our target will dictate what type of species or what population we'll see at our plasma sensors. So this is output as a function of time in microseconds. Again, positive bias, negative bias, or grounded target. And what we see here, we had two different plasma sensors retarding potential analyzer, and you could see that we're detecting this ion population in only one of them. We believe this is due to just a beaming effect where our other plasma sensor was a little off-center. And these peaks actually corresponded to the constituents in our plasma. So we were able to pick out like the iron peak and carbon and actually do kind of a pseudospectroscopic measurement. For a grounded target, you'll notice that the signal strength is lower. But you'll also see that we're now not beaming the plasma as much, but it's expanded out. And then for the electrons, you'll see basically, again, these negative signals because we're biasing it negatively. So you see this interesting positive peak followed by these two strong negative peaks. And we believe that we're actually seeing negative ions in addition to some secondary electron emission. And this gets much more complicated. This is some of the data analyzed by Lockheed once you actually start looking at specific spacecraft material. So the previous plot was just basic tungsten. This is for solar panels, solar cells, optical solar reflectors, either standard or conductive. And you'll see lots of signal, but uninterpreted as of this point. We're not quite sure what these signals are actually telling us. We do believe we're seeing quite a bit of negative ions, which is, again, very dependent on the type of target that we're actually impacting. And then finally, a little bit of RF data. Again, this was really what we were pushing for at the beginning of this project. This is what Maki et al. Published many years ago using a Japanese facility to try to understand how do these particles, when they're impacting spacecraft, actually create RF emission, and can that emission actually find its way into the spacecraft? So this is frequency versus time, again, another spectrogram, and you might remember way back that theory when I put a spectrogram showing kind of that chirp-like pulse associated with the plasma. And what this is showing again is that it's consistent with the theory that was put forth in the literature that we're seeing the lower frequencies at a later time. And so again, this is data collected by the patch antennas showing some type of emissive process. And once we look at all of the data, which included thousands of individual shots, you can plot particle mass as a function of impact speed and see exactly where is that RF emission being detected, where is the optical emission being detected, and where is the plasma basically being detected as well. So all these points indicate the type of particle, so again, as a function of mass and speed. And it's color-coded. Blue is a detection that had some type of optical signal associated with it. The orange is plasma, and then the green circles indicate where we saw RF. And so you can also take these data and plot as a function of rate, RF detection rate as a function of speed, and do a cumulative distribution for two different types of target material and bias. And you'll see that, really interestingly, as the speed gets higher and higher, you're more likely to detect RF, which you can see on this plot, which is a little bit better shown in the cumulative distribution. And so this was really an important finding. Again, we weren't the first to look at this, but the community basically put forth is that for the plasma being created, both the debris and the meteoroid will create that plasma, but it's only the very fast meteoroids which can create plasma that can actually emit in the radio frequency. And so we believe this is now correlated to this transition between where it turns from a partially ionized plasma to a fully ionized plasma, again, not fully understood. But what this has done is really focused our attention on the meteoroid population and really understanding how particles this small, 10 to the minus 14, 10 to the minus 15 grams, can actually create some type of RF wave that can find its way into the spacecraft electronics and potentially cause some type of anomaly. And so what we've done is basically, or I should say our colleagues at JPL have done, is taken that RF frequency data and basically tried to estimate what happens when a particle going 60 kilometers per second at particular masses actually impacts the spacecraft. And so what you see here is some of the ground-based tests that have been published. And then, so let's say a femtogram-sized particle going 40 kilometers per second. And then if we extrapolate that up to a nanogram going 60 kilometers per second, or a microgram going 60 kilometers per second, the detected electric field is about 10 to the minus 3 volts per meter. If you go all the way up to a microgram, that's 10 to the 7 volts per meter for electric field. And you can also do the same for peak power. This is concerning because spacecraft are currently spec'd to about 10 volts per meter, 10 to 100 volts per meter. So what we're finding is that we are orders of magnitude greater in terms of electric field to what spacecraft are currently spec'd to. And again, this is a new result out in the community, so it's something that people are now starting to talk to, people at Loral and Lockheed, to try to give them an indication of what types of fields are actually being measured. But again, remember, we have to extrapolate. So this is the electric field as a function of speed, or threat radius as a function of speed. We have to extrapolate because we're not able to actually reproduce that size regime in the laboratory. Okay, so I know that this topic is maybe slightly off topic for what a CEDAR tutorial normally is, but again, we want to kind of bring this into the community in terms of a lot of the research that was done here at CEDAR over the past decade or so is now being used, and we're extrapolating that data to try to really understand what exactly is happening when these particles actually impact spacecraft. So in the past, we've used these high-power large aperture radars to try to detect the plasma form when these particles come into our atmosphere. We use that with modeling to basically back out meteoroid masses and densities, as well as determine fluxes and velocities. And now, over the past, I would say, 6 to 7 years or so, the community has kind of shifted focus, and now what we're doing is trying to say, okay, now that we kind of have a better handle on what types of particles are actually out there, how do we then take that and actually try to figure out what happens when these really tiny particles that in the past no one has ever worried about before impact spacecraft? Can these really tiny particles create plasma that could then emit and cause failures and maybe explain some of those unexplained anomalies back on that database chart that I showed? So I would say that this is something that I would love for this community to get more involved in. I would say that the physics is still not very well understood at all. We have remote sensing of plasma. Again, as I mentioned, this has been a great benefit to understanding this process. But what we need to do now is really look at both space-based data as well as these ground-based data to really try to understand the electrical effects. And so multi-sensor approach, I think, is the way to go. So there might be other ideas out there that we can incorporate. We know that there's a strong dependence on things like how fast the particle's going, how are the spacecraft biased, what type of target are we impacting. And I would say definitively now, which is a new result in the community just in the past few years, we've shown that these particles, these plasmas, can actually emit in the RF, and that RF wave can find its way into the spacecraft. So I would say the implications are still fairly unknown. And I'll leave you with a fireball. This is very old data. This is from the Draconids back in 1992. This, again, was captured by, back in the day, we didn't have the cell phones, but a video camera. And it basically traversed this path over West Virginia. The recovered meteorite had a mass of about 12 kilograms. They believe it was going about 15 kilometers per second. Initial radius estimates around 100 centimeters or so. And the interesting thing about this impact is that it hit a car. So meteoroids don't only hit satellites, they unfortunately also hit things on the ground. Okay, thank you.